Thermal stresses. So thermal stresses are also called as a secondary loads. So what are the secondary loads? These loads are generated due to the temperature and some kind of displacement imposed on the piping system, like thermal expansion and contraction, tank settlement, anchor movements, vibration, etc. So secondary loads are cyclic in nature and results in a fatigue failure. So we can say that secondary stresses have displacement driven, one thing. Second, these are cyclic in nature. These are self-limiting stresses. When after displacement, the stresses in the line will be reduced. So mode of failure for this from the secondary stresses is a fatigue failure. Okay. Now, computed displacement stress range. Computed displacement stress range SE can be calculated through this formula, which is SE is equal to SA plus SB whole square plus 2ST whole square under root. This the axial stress range due to displacement strain. SA. How we can calculate this? SA is equal to IA FA over AP, where AP is the cross-sectional area of the pipe, FA is the axial force range between any two conditions being evaluated. IA is the axial stress intensification factor and AP is the cross-sectional area of the pipe. Similarly, the bending stress range due to displacement strain SB can be calculated through this formula, where MI whole square plus MO whole square divided by Z under root. So SA is equal to axial stress range due to the displacement strain. SA is equal to IA FA over AP, and SB is the bending stress range due to the displacement strain. ST is the torsional stress range due to displacement strain, and this ST can be calculated as torsional stress range due to displacement. ST is equal to IT MT over 2Z, where MT is the torsional movement range between any two conditions being evaluated. Z is the sectional modulus of the pipe. IT is the torsional stress intensification factor. Allowable displacement stress range SA, it can be calculated through this formula. SA is equal to F into 1.25 SC plus 0.25 SH, where F is the stress range factor or cyclic stress reduction factor. It can be also known as FM, the maximum value of the stress range factor, which is 1.2, or otherwise we can take it as 1. SC is the basic allowable stress at minimum metal temperature, okay, which is expected during the displacement cycle under analysis, which is, we can say that 120 ksi maximum. So SH is the basic allowable stress at maximum metal temperature expected during the displacement cycle under analysis. We can say that 20 ksi maximum. SL, the stress due to the sustained load in system where the support may be active in some conditions and inactive in other conditions. So these are the values that we normally consider when we have to calculate the allowable displacement stress range. So this SA is equal to F into 1.25 SC plus 0.25 SH. We'll calculate from where we got this formula. We'll drive this formula in next slide. Computed displacement stress range, which is SC, which shall not exceed the allowable displacement stress range SA. Here SA is equal to F into 1.25 times SC plus SH minus SL. When SH is greater than SL, then SH minus SL is the liberal stress. So code allows these two allowable stress range. One is without liberal stress, other one is with liberal stress. So we'll discuss in next slide what is liberal stress and whether we have to use it or we don't have to use it. Thermal stress, allowable displacement stress range SA. How to drive this formula? To drive the formula of the allowable displacement stress range SA, we shall take an example of the pipe with fixed end on both sides, as shown in the diagram, having temperature T inside. Let's increase the temperature of the pipe and see how stress and strain develop in the pipe. As you can see the stress strain graph, compressive stresses are along the plus y-axis and tensile stresses are along the minus y-axis, while the strain is along the x-axis. First, let's increase the temperature of the pipe from T1, which is equal to 0 at point O, to T2, which is equal to 300 degrees centigrade, and it will create the thermal stresses and strain in the pipe from point O to point A, which follows the Hooke's law. Means linear relationship between stress and strain till point A. As pipe both ends are fixed, hence the stresses developed in the pipe shall be compressive in nature. If we shall further increase the temperature of the pipe from T2 300 degree centigrade to T3 600 degree centigrade, it will increase the strain in the pipe at some constant value of the compressive stress till point B, as shown in the graph in the red line. It means the yielding strut in the pipe due to high temperature, and now if we shall reduce the temperature of the pipe, and it will follow the same slope as from point O to A, means the same Hooke's law, but after reducing temperature from T3 600 degree centigrade to T4 300 degree centigrade, it will touch the strain axis at point C, as shown in the blue line graph. It is due to the strain hardening in the pipe, strain hardening in the pipe material, and we shall further cool it down till T5 is equal to 0. It will touch the tensile axis at point D. Now if we look the stress strain graph closely, the material of the pipe shows same yield stress in compression and in tension. Means when we increase the temperature, the compressive stresses develop in the pipe, or if we reduce the temperature, the pipe becomes relaxed and expansion starts due to reduction in thermal forces. Hence each material has two yield stress values. One is in cold yield stress conditions and other one is in hot yield stress conditions. So we can say that 2SY is equal to SYC, which is the yield stress in cold condition plus yield stress in hot condition, is equal to 2SY, which is the yield stress of the material. As we know, the allowable cold stress is equal to 2/3 of the yield stress in cold condition. Similarly, allowable hot stress is 2/3 of the yield stress in hot condition. If we'll calculate the yield stress in cold and yield stress in hot from this, it will be equal to 1.5 times of SC is equal to SYC. Similarly, 1.5 times of SH is equal to SYH. And if we'll input this in SA, total is equal to 1.5 SC plus 1.5 SH into factor of safety. It means based on the ASME B31.3, after applying the factor of safety, a total allowable stress will get 1.25 times of SC plus 1.25 times of SH. And as we know that sustained stress is SL is less than SH. So allowable displacement stress range SA is equal to 1.25 times of SC plus SH minus SL into F, where F is the cyclic stress reduction factor. If you further evaluate this equation, so SA allowable is equal to 1.25 times SC plus 1.25 times SH minus SL into F. And further, if you evaluate this equation, we can come up with the 1.25 times SC plus 0.25 times SH plus into SH minus SL. Here SH minus SL is called the liberal stress when SL is greater than SH. So allowable expansion stress range without liberal stress when SL is greater than SH will be F into 1.25 times SC plus 0.25 SH, which is our required formula, and this formula is applicable for low pressure piping up to 2500 rating. Similarly, the allowable expansion stress range when the liberal stress SL is less than SH, this formula becomes like this: SA allowable is equal to 1.25 times SC plus 0.25 SH plus SH minus SL into F. So this is called the liberal allowable stress or allowable displacement stress range based on the liberal stresses. For high pressure piping in chapter 9, S allowable is equal to F into 1.25 times SC plus 0.25 SH. This is used for high pressure piping. We cannot use high pressure piping in system the liberal allowable stresses. This is as per the code. Now the question is whether the thermal force is independent of pipe length or not. To prove that, the thermal force is independent of pipe length, let's take a pipe piece of length L1. When the thermal force is applied due to change in temperature, the length of the pipe will change from L1 to L2. So the change in length shall be delta L. As we know, stress is directly proportional to strain within the elastic range, means it obeys Hooke's law. So sigma is directly proportional to strain, and sigma is equal to E epsilon, which is Hooke's law. This is equation 1. So we also know that sigma is equal to P over A, and as in our case P is equal to F, sigma is equal to F over A. From equation 1 we can say that E is equal to sigma over E. From equation 3 and 4 we can conclude as E is equal to F over A over E or epsilon. And as we know, the strain is change in length to the original length, which is epsilon, mean strain, and we also know that change in length due to thermal force is delta L, alpha L delta T. So if we'll input from equation 6 and 7, we can conclude it that strain is alpha L delta T over L. Here we can cancel out L with L, so the strain in our case it becomes E is equal to alpha delta T, which is equation 8. Now from equation 5 and equation 8 we can conclude easily that E is equal to F over A divided by alpha delta T. Now from here if we will calculate the value of F, which is EA alpha delta T, we can get that the force is independent of the length. Means whether the pipe length will be 1 meter, 100 meter, the thermal force remains same. Hence, we can say that the thermal force is independent of the length. Here is a question that thermal stress is independent of pipe diameter or not. To prove that thermal stress is independent of pipe diameter, let's take two pipes with different diameter as shown D1 and D2 with area A1 and A2 of same length L. Let's apply same temperature and pressure in both the pipes and calculate the thermal stresses in both the pipes due to increase in temperature. Again, the stress in the pipe A1 is equal to sigma 1 is equal to F1 over A1, this is equation 1. So the thermal force F1 will be is equal to EA1 alpha delta T. Thermal force for area A1 or for the pipe A1. This is the first force. So from equation 1 and 3 we can say that sigma 1 is equal to EA1 alpha delta T divided by A1. So A1 is cancelled out with A1, so we'll get sigma 1 is equal to E alpha delta T, which is equation number 4. Let's calculate the stress in the pipe A2. Similar way, sigma 2 is equal to F2 over A2. So thermal force in pipe A2 will be F2 is equal to EA2 alpha delta T, and from equation 2 and 5 we can simply say that the sigma 2 is equal to EA2 alpha delta T divided by A2, and A2 cancel out by the A2, and sigma 2 will be equal to E alpha delta T. Here sigma 1 based on the equation 4 and 6 we can say that sigma 1 is equal to sigma 2. It means thermal stresses in both the pipes with different diameter will be equal for same length under same temperature and pressure condition. So we have proved that the thermal stresses are independent of the pipe size or diameter. Now this is the last and the 10th stress we need to discuss here, pipe or in piping system, that is called the fatigue stresses. So what is fatigue? By definition, it is progressive material damage in a pipe that occurs when pipe material is subjected to cyclic loading. Why we do fatigue analysis of piping system? Just to determine the endurance limit or the lifespan of the piping system, we have to do the fatigue analysis of the piping system. The stresses which causes fatigue failure in the piping system are the peak stresses. This is very important. Fatigue is another type of the stresses in the piping system. As the pipes are in use, they experience repeated pressure fluctuations as well as temperature ramp ups and cool down. These cyclic lives is common metric for determining a pipe's lifespan. Compromise pipe strength over time. So fatigue stresses are considered under secondary stress due to displacement driven. These are cyclic in nature and mode of failure is fatigue. Fatigue stresses are basic of two types. Number one, static fatigue. This is due to the primary stresses, that is weight of the pipe, weight of the insulation, inadequate support in the piping system. These are the causes of the static fatigue. Second one is the dynamic fatigue. So dynamic fatigue, it is because of the fatigue due to the thermal fluctuation. Second, fatigue due to the pressure fluctuation. Third one is fatigue due to the vibration, and this vibration we can say that it is because of FIV, flow induced vibration, AIV, acoustic induced vibration, due to PSV pop-up, two-phase flow, due to slugging, due to rotating equipments, due to low pressure and steam condensate lines. All these are causing the vibration in a piping system, and consequently it will create a fatigue in a piping system. And the fourth one is fatigue due to wave motion. This is normally in offshore. So it must be noted that the fatigue life of a material operated at elevated temperature may be reduced. So fatigue analysis shall be in accordance with ASME pressure vessel section 8 division 3 requires that the stress concentration factor be used in computing the cyclic stresses. So creep fatigue interaction effect shall be considered when the number of cycles exceeds 100 in elevated temperature service. As per ASME B31.3 section K304.8.3, the pressure stress evaluation for fatigue analysis, we can use this formula. So for fatigue analysis of straight pipe, this equation may be used to calculate the stress intensity at the inside surface due to only internal pressure. Here P is the pressure, D is again the diameter, C is the total allowances, all these things, S is the stress value. So the next is the allowable fatigue cycles. This is under ASME B31.3 section W302.1 fatigue damage due to cyclic stress. We can calculate the fatigue damage due to cyclic stress or number of cycles we can calculate with this formula. The maximum stress range SC shall be computed in accordance with SC, which we just studied in the previous slide. SC is equal to SA plus SB whole square plus 2ST whole square whole under root, and meet the allowable displacement stress value, which is SA that we had just studied, F into 1.25 times SC plus 0.25 SH, where F is the 1. So fatigue damage shall be computed with this formula. Here we have studied all 10 types of stresses that the piping system face during its life. Hope you understand all these things, and next part will be part 3. We will do the practical stress analysis on Caesar software. Thanks for watching.